So last time we did Chinese remainder theorem, which is in general form it is that you are given a system of linear equations in one variable. X is the single variable and the moduli are all different. In fact, they are co-prime, mutually co-prime numbers, ni's. So this theorem says that there will always be a unique solution. And the solution is given by that expression. And then we started analyzing how many primes are there in the range 1 to x, which we'll finish today. Any questions till now? Okay, so what we will prove is that the number of primes between 1 to x, this prime function pi x, its density, which is pi x by x, it is around, it is between 1 by log x and 5 by log x, where log is to base 2. Okay, in particular it says that the density is very high. Okay, it's 1 over log x, which is excellent for any practical application in computer science. This kind of expression was first conjectured by Gauss. In 1800s, he did calculations by hand, and by looking at the table, he guessed it. But the way it was proved, that's a long history. You can read it on Wikipedia. Okay, so this used to be a conjecture by Gauss that pi x is around 1 over log x. Simply by looking at the values of this for various x's, from x to some x equal to 1 to x equal to thousands, he manually tabulated the values, which is why this strange expression. And then indeed it can be shown. So for computer science, it's enough to just do the estimate, and this will require some lemmas. So first lemma says that 2n choose n is at least 4 to the n by 2n plus 1. So proof of lemma 1 is just that sigma 2n choose I is 4 to the n, right? In which you have to show that the middle term is the largest, which is 2n choose n. So which means that the largest term is at least the average. Okay, that's the proof. This is the maxima. Is this clear? So all these things you know, so you can finish this proof. Second lemma is that if you look at the prime powers which divide 2n choose n, they never exceed 2n. Okay, although 2n choose n is very large, still the prime powers are small. So why is that? So the idea is you look at this expression, so you are multiplying numbers n plus 1 to 2n, n plus 1, n plus 2 dot dot 2n, and dividing by the numbers, basically n factorial. So 1 dot 2 dot 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 n. So the prime powers which divide the denominator, what happens to them? So say p raised to v, p raised to I divides x for some x 1 to n. What can you say about that? Is it guaranteed that this p raised to I will survive, will also divide 2n choose n? But what can happen is p raised to I is present in the denominator, then it is forced to be present in the numerator also, right? Because the denominator has to divide the numerator. But it's possible that p raised to I is exactly present, and so both of them cancel and p is absent. P doesn't divide 2n choose n. Right? In fact, that is what usually happens. So if p raised to I divides x between 1 to n, then there exists a y in n plus 1 to 2n such that p raised to I also divides y. Why is that? Well, because p raised to I is smaller than n, right? So if you just look at x plus p raised to I, this is still in the range. This is still below 2n. So there will be some number after x which will be between n plus 1 to 2n, which will also be divisible by p raised to I. So what happens is these higher powers which divide the denominator, they also divide some number in the numerator and they get cancelled. So using this you can deduce that the surviving p powers which divide 2n choose n. So if p raised to v divides 2n choose n, then basically it is bigger than n, and it divides some number y which is large, bigger than n. Okay, so prime powers which actually survive in this division, this p raised to v must be larger than n, and it divides some number which is between n plus 1 to 2n. So in particular it is smaller than 2n. Is that clear? This was too quick, but you can work on this and finish the proof. The idea is basically this, that if p raised to v is dividing 2n choose n, if it is surviving in this ratio, it cannot be larger than 2n, because all the extra things, they are actually common, so they get cancelled. So only small p raised to v's remain, which are between n plus 1 to 2n, because they don't have anything to cancel within the denominator. So that's a quick sketch for lemma 2. So all these prime powers are actually smaller than 2n, or less than equal to 2n. And let's do quick sketch of lemma 3. So here you have to show that product of primes up to n never exceeds 4 raised to n. How do you show this? So for example, if you take n to be 5, then the product is 1 times 2 times 3, and you can also multiply by 5. So 1 times 2 times 3 times 5, you can see that it is smaller than 4 raised to 5. Okay, the product of primes is usually much smaller than 4 raised to n. It's actually even smaller than 3 raised to n, but that proof will be longer. So let me stick to 4 raised to n. How do you show this? So this will be shown by induction. N factorial is smaller than what? No, it's not. It's much, much bigger. Yeah. If it was that easy, then that was in assignment 1, I guess, right? N factorial. N factorial is almost close to n to the n. But this is 4 raised to n, so we need this for a good estimate on density of primes. Yeah, so this is non-trivial, but not hard. What you do is we'll do induction. So base case of induction is done. As I just said, you can check for n equal to 5. That is satisfied. So now let us assume induction hypothesis. Assume it to hold for, let's say, n equal to 2m plus 1. No. Let's consider n equal to 2m plus 1. Let's consider n to be odd basically and look at the product. Of primes up to 2m plus 1, that's n now. So this will be less than, so we divide this into two kinds of primes. Actually what I want to do is I want to invoke lemma 2 here, I think. So I want to divide this into two kinds of primes, primes which are smaller than m plus 1, and the other product is primes which are between the remaining ones. Okay, these two I consider. And what do you do next? So the first product you will do induction, and the second product primes between m plus 2 and 2m plus 1. What do you do with them? Okay, let's do the first one, that is 4 raised to m plus 1 by induction, right? Because m plus 1 is strictly smaller than n. So by induction we can estimate this by 4 to the m plus 1. What do you do with the second one? So there I want to write the following. It's smaller than 2m plus 1, choose m. Is this correct? Sorry? In the first step what? The induction hypothesis is product of primes up to n is 4 to the n. Sorry? I don't understand. P is less than equal to m plus 1. Well, let's try to understand. First bracket is P less than equal to m plus 1, and the second one is P greater than m plus 1. Before the bracket less than sign. So these are the primes. Is this fine? 1 to m plus 1? That's not fine. Why not? Oh, you are saying it's equal. Yeah, that's fine. I mean, that doesn't matter. Sure. That isn't a problem. The problem is what do you do with the second factor, the second bracket? I want to claim that this is at most 2m plus 1 choose m. Can I say that? Sorry? Right. So this is actually not lemma 2. This is something even simpler. So a prime which is bigger than m plus 1 and smaller than 2m plus 1 that will not appear in m factorial, for example. So if it is not, since it doesn't appear in m factorial, it only appears in the numerator product, which is m plus 1 dot 2m plus 1. So hence it will divide 2m plus 1 choose m. That's the argument. Since p in the range m plus 1 dot 2m plus 1 for all p divides 2m plus 1, choose m. Is this clear? Because 2m plus 1 choose m is again m plus 1 dot 2m plus 1 divided by m factorial. This p will not divide m factorial, but it will divide the numerator, so it will divide this binomial 2m plus 1 choose m. So if you just carelessly estimate the product of primes by 2m plus 1 choose m, it isn't a mistake. It's just a very lazy estimate. Right, so we have this. So now we have replaced primes by something much easier. Right, we have now these two expressions which are much easier. They are more explicit than just product of primes. And what do you do now? So this is 4 raised to m plus 1 times I say that this 2m plus 1 choose m is at most 4 raised to m. Is this fine? Can you show this? 2m plus 1 choose m is at most 2 raised to 2m. What is the proof? The proof is that this, again you look at the sum of all binomials, it will be 2 raised to 2m plus 1. But then you note that the main terms, largest terms are 2m plus 1 choose m and 2m plus 1 choose m plus 1. So there are two terms and then other smaller terms, all of which sum up to 2 raised to 2m plus 1. So you can divide that by 2. Is that clear? That is why I wrote 2 raised to 2m, which gives me 4 raised to 2m plus 1 overall. Okay, so the product of primes up to 2m plus 1 we have shown is at most 4 raised to 2m plus 1, which completes the induction step. Right, so we have the proof by induction. Is this proof complete or is there any other step remaining? There is one more step, n can be even. So n can be 2m. What happens in this case? So in this case, you are looking at product of primes less than equal to 2m. But trivially, this is the same as product of primes up to 2m minus 1. Right? This is prime. So it can't be 2m. So actually, even reduces to odd. You can just as well do the 2m minus 1 thing, for which by induction you will get 4 raised to 2m minus 1, which clearly is less than 4 raised to 2m. Right? So here also the induction step holds. That's the induction hypothesis. Is this clear? So both even and odd n are covered by induction steps, and hence overall induction holds. So we have the result. That finishes lemma 3. Okay, so lemma 3 was that product of primes up to n is at most 4 to the n. Is this clear? Okay, so now we are ready to get this prime density estimate, which still looks very mysterious. I mean, these lemmas, what are they to do with pi of x, right? So this is still, even at this stage, it is non-trivial, but you will see that now it will simply follow. So here are the steps. That's the density estimate theorem. So let us now prove this. So first we will show the upper bound. So pi x less than 5x by log x part. Let's do that first. So for this, the idea is look at lemma 3. Right? Lemma 3 is saying that the product of primes is kind of small. And from here we want to deduce that the number of primes is also kind of small. I mean, we know that number of primes cannot be more than x because there are only x numbers. But what we want to show is actually it's smaller than x. It's 5x by log x. So that will follow from lemma 3 as follows. So we'll use lemma 3. So there are number of primes in the range square root x to x is, by the definition of pi, it is pi of x minus pi of root x and so what this means is if you look at the product of primes, less than equal to x. So look at these primes which are bigger than square root x, right? They are how many? Pi x minus pi of square root x. So this product is at least this much. Let's call this something, maybe n. Okay, so product of primes up to x, we just focus on the big primes, which is bigger than square root x. So that is square root x raised to pi x minus pi square root x. And you have an upper bound of 4 raised to x. So now from this actually you will be done. If you just take log both sides, you will get the answer. So this means that pi of x minus pi of square root x times log of square root x is less than 2x, right? And that will give you a bound on a pi of x. Pi x is less than something. So what is that? Pi of x is less than 4x by log x to base 2 plus pi of root x. Right? So the difference is at most 4x by log x. That is what I have written here. Is that correct? And but then you have pi of square root x sitting. You replace it by what? By the trivial, which is square root x. Right? You know that number of primes cannot exceed x, or cannot exceed the range. So you get 4x by log x plus square root x. And this is always smaller than 5x by log x for x greater than or equal to 2. Okay, so we have shown that pi x cannot exceed 5x by log x. Is this fine? That's the upper bound. It holds for all x's. So this is highly non-trivial because pi of x by definition is smaller than x, but here we are saying that it's even smaller than, it is far away from x actually. Right, but this was still okay. The harder thing is the lower bound, that well at least you have these many primes, right? So that's the more interesting thing for us, that how many prime numbers are there. So let's do that next. Let's show the lower bound on pi x. So what do you think, which lemma will give you the lower bound on pi of x? That will be the remaining lemmas, which is lemma 1 and 2. Okay, lemma 1 says that this 2n chosen is a large number, and lemma 2 says that it contains these primes p's. So from this we will actually deduce that there are many primes. So let's see how. It's not completely trivial, but you will see that it can be done in an elementary way. So we'll use lemma 1. So first you write 2n choose n as product of primes. Okay, so basically this is the prime factorization of 2n choose n. All the primes that divide, the distinct primes that divide 2n choose n with their exponent Vp. That's how it factorizes. That's the kind of the definition of the RHS. And what can you say about the upper bound of p raised to v? How big is that? That was lemma 2, right? It's 2n. P divides 2n choose n. And so can you give an easy estimate on this product? It will be 2n raised to something, which is in the exponent you will put the number of primes that can divide 2n choose n. How much is that in terms of pi? Can a number bigger than 2n, can a prime bigger than 2n divide this? So it can at most be pi 2n. Right? So this product is, 2n choose n is at most 2n to the pi 2n. Right? This is all we have reduced here. And you know from lemma 1 that this is large. You know that this is, or maybe I should first take the log. We have shown that this is greater than or equal to 4 to the n by 2n plus 1, and then we take log. So what will this give you? This will give you so 2n minus log of 2n plus 1 is less than or equal to 2n log of 2n, right? Log of, pi of 2n here. Which implies that pi of 2n is at least wait. Okay, I guess this is fine. Is this okay? This is what we get. That pi of 2n is at least 2n by log 2n with some error term here. But the error term you can see is not too large. It is log of 2n plus 1 to base 2n. So it cannot exceed 2 ever. It's strictly smaller than 2, right? So this is the estimate. So from this, in general, for a general x, what you will get is, for general x, for arbitrary x, pick an n, pick a natural number n such that you get x sandwiched. Okay, so x can be, x can be even, or it can be odd, or it can also be any real. So you can always sandwich it between two even numbers, and then you apply the above inequality. So what that inequality says is that pi of x is greater than equal to, first, I mean, obviously you have greater than this thing, greater than pi to n, at least pi to n, and then you use that expression. Which is, now you substitute, you try to substitute x here, so you will get, so not exact, but lower bound you can now deduce. So 2n is, yeah, you need to write 2n greater than or equal to x minus 2 in the numerator, and for the denominator you need 2n less than or equal to something, so which is x, so log x here, minus, let me just write this. Okay, you will get this expression. So now you have on the left hand side pi of x, on the RHS you have a function in x. You simplify and get this easy conclusion that this is greater than x by log x minus 2. Okay, so between 1 and x there are always these many primes, x by log x, and at most 5x by log x. So both the sides we have now. Any questions? Okay. So this is good enough for all our computational applications in cryptography, coding theory, whatever. One interesting number theoretic fact from here is you can deduce the presence of a prime in small intervals. So for example, can you deduce from here that there is always a prime between n and 6n? That's a corollary of this. Maybe x, what did we have there? X greater than or equal to 5, so maybe that. Where did we get 5? I think that was needed here in this calculation that you use. When there are these functions, to actually say that it is greater than or equal to, you need x to be sufficiently large, so you can check that that 5 works. So as a corollary you get that there is always a prime between a number and 6 times that. Do you see this? How do you show this using the density theorem? What is the number of primes between x and 6x? Pi of 6x minus x minus pi x. Right, and now you can use both the upper and lower bounds to estimate this difference. So this, for example, you want basically a lower bound on this. So pi of 6x will be at least, so let me do this approximately. So this will come out to be at least 6x by log x. On the negative side, you want to upper bound. So upper bound we proved was 5x by log x. So in particular, this will come out to be positive. Okay, so no matter what x is, this difference is always positive. So which means that you will always find a prime in x and 6x, which is an interesting thing. There is no easy way to prove this directly, that you can find primes in these small intervals. Can you make the interval smaller? Can you say that there is always a prime between x and x plus 10? Yeah, those things will not work. Even if I say there is always a prime between x and x plus 1 billion, somebody can run a computer simulation and always find that, well, there is an x for which there is no prime in this interval. Okay, so empirically you will be able to find these long gaps where primes will not exist. So those things are not true, but the best known result is x and 2x. That can be shown. That is called Bertrand's postulate. I will not show this, but you can do it as an exercise. Or read the proof. So proof by Chebyshev. So this says that for all n, there exists a prime in n and 2n. Okay, so in any interval which is of this type, a number and twice that, you will be able to trace a prime. Smaller results are not known. They are famous open questions. For example, there is this open question of Legendre from the 1800s, that for all n, interval between two squares there is a prime. Okay, so Legendre conjecture says that if you look at the sequence of squares, there is a prime in every interval. Why is this not a conclusion of Bertrand's postulate? Yeah, because gap between two squares is smaller than half. It's around square root, right? N plus 1 square is less than, definitely less than 2n square. It's something like n square plus n square plus 2n. So as in terms of x, it is like x and x plus root x, right? So it's a much smaller gap. These results are not known. These are conjectures. There is no empirical counterexample for this. If you list squares, you always get primes in every interval. So that you can try to solve as a homework exercise. Any questions? Okay, so then we can quickly do some applications of what you have learned so much in number theory. Which is basically in cryptography. So, yeah, cryptography, and there are many other applications, but we can't do everything in discrete maths. We'll just sketch some applications, the rest you can read. So what is cryptography? It is two people want to communicate over a channel which is being watched by many other adversaries, right? So goal is that you should be able to communicate, but they shouldn't be able to deduce what you are talking about. So basically the issue is to do with security. You want to have a protocol which is as secure as possible. Obviously it cannot be mathematically secure, that those things are kind of impossible, but it should be practically secure. Practically you should have confidence that it can't be broken, which is how all the internet security works. So the goal is that transmitting messages over an insecure channel such that, so first is, or let's say the zeroth thing is that if the channel makes some errors, for example, howsoever you communicate physically, whether by air or by wire or whatever, there are always errors introduced. Or say in a USB or hard disk, wherever you store information, there are errors. Okay, nothing is error free. So you want it should be error correcting. Errors can be corrected. And the second thing is that adversaries should not be able to understand. Right, these are the two main issues whenever you are trying to transmit message. So first is to do with error correction, which we will not discuss in this course, or maybe one thing maybe we can discuss once we have done this finite fields, etc. So at least we'll not discuss it now. The second thing is what we want to discuss now, which is the issue of security. So those are the two main concerns. So this is with security. And first is error correction. So error correcting codes. Now error correcting codes are extremely important, because if they were not there, then computers will not work, because every device in computers is making errors constantly. So which means that your data will be corrupted within few hours, and you will not be able to, if you don't have a method to make sense of corrupted data, then you cannot do anything, right? So before computers were implemented or physically created, before that this error correction mechanism was invented, and that mostly is an algebraic method. So we'll do that one day. Second is assuming that the channel is perfect, there is no error, still you want to hide things from an adversary, right? So these methods, again, the most important methods are algebraic, and we will discuss some number theory based methods. So don't have much time to do everything. Okay, let's anyways discuss some basic definitions. So we'll have two players or two parties. The first is A for Alice and the second is B for Bob. And third is the adversary, which is E for Eve. Okay, and there is a channel which models anything. It can be paper being transmitted, being handed over by post, or it can be wire, or it can be electromagnetic waves or whatever, or hard disk. So that is what this line denotes. And I think this is, we'll always say that Alice wants to transmit something to Bob. So you can also think B for a bank. So A can be a customer, Alice, say on a smartphone, and B is the bank. So the secret things Alice will want to send to the bank. Right? That is the situation which is happening all the time these days in most of the applications. But it can be also be two-way. Maybe Bob also wants to send a secret to Alice. And then there are many people in the middle who are watching this conversation, right? You want them to not be able to deduce anything. So the question is, how is it possible if Eve is looking at each and every bit of the message, how can Eve not know but Bob know? Right? So do you have any idea? How is this possible? What is the difference between Eve and Bob? Yes, so the most basic idea would be that Alice and Bob meet early on and they share some secret, right? And then the remaining communication happens with that secret. So Eve would not have an idea what they are discussing. So, which gives us some notation, which is A wants to send, let's use the full form here. So Alice wants to send B a message M, and this you can think of simply as a string with n bits. Okay, but usually it will be an English or alphanumeric message, but then you can code it as 0, 1. Right? You can say that A is whatever, you can take Unicode or some standard encoding. So all the punctuation marks, alphabets, numbers, everything can be coded into, let's say, 5 bits. Right? So you have these blocks of 5 bits, and you can send in any language anything. So ultimately, the message M is just a string, models huge text that Alice wants to send. So 0, 1 is called the alphabet. Okay, our alphabet is binary here. And N is the length of the message. What else is there? So Alice will encode it to get C. So that's the code. That's the code C. So we call M plain text. And we call C ciphertext. Okay, and how to convert M to C is the hard thing. It's an algorithm which is encryption algorithm. Right, so the encryption algorithm, as suggested correctly, Alice and Bob will share a secret S, encryption algorithm will use S and M to produce C. So encryption algorithm E uses S and M to get or to compute the ciphertext C. So this S is the secret. Okay, so then this is sent to Bob over the same channel. Assume that the errors are taken care of by some other algorithm that we will discuss few weeks after. What can Bob do with C now? So there will be another algorithm which is the decryption algorithm, which will convert C back to M using S. To compute M. And of course, this has to be done, I mean, the decryption algorithm should be powerful enough to uniquely compute M, right? Otherwise, it won't be of any use. I mean, say you are in a war, if you send that the missiles have to be fired at 10 a.m. and then on the other side, they read it as 11 a.m., it's not good. Right? So you want the message to be exactly uniquely recovered. There should be no error in that, right? So both these things are precise algorithms. So everything is now kind of dependent on this secret, right? What will be the secret and then what will be the encryption? Correspondingly, there will be a decryption. So do you know of any secrets? If you have to send something to your girlfriend, let's say girlfriend number 1 and girlfriend number 2 should not understand. So in that case, do you know of a secret way to, or what should be the S in encryption algorithm? So a method which is thousands of years old is what is called substitution cipher. So what you can do is you can map the, let's say, alphabet, English alphabet A to Z to a permutation, right? So A is, let's say, associated with B, B with C, C with D, and so on, and then Z with A, and that is the secret. Okay, so now when you write letters, you write applying the permutation. So that's the encryption, and decryption will just be inverse permutation. It's also called Caesar cipher because old kings were stupid and they were using this. So here the setting is S is a permutation on sigma. Let's say it's from A to Z to itself. Okay, so pi is the secret, and encryption is simply you take the S, M, and C will be, the ciphertext will be just pi applied on M. Okay, so for example, ABC will just become under this cyclic, the forward shift, it will become BCD. And decryption will be will just be pi inverse on C, which will be pi inverse of pi of m. So you will uniquely get m, right? So this is basically everything is dependent on this permutation being secret between Alice and Bob, right? If permutation is not secret enough, then there is no security in this. If the permutation is secret, is this secure? It's not secure. Why not? Sorry? No, fine. So that isn't a practical argument. Number of permutations is 26 factorial. How much will Eve search? She will get old and die. Right. Yeah, so the problem is this will be fine if the messages were completely arbitrary strings, right? Then it is mathematically fine. It will depend on whether the permutation is guessed or not. And since the permutations are 26 factorial, I mean 26 factorial is small, is a lower bound. It will be much more, because you have small a to z, capital A to z, punctuation marks, numbers, all that. So this is at least more than 26 factorial. I mean, this is at least 26 factorial, possibly much more, but 26 factorial already is very large. It's something like 26 to the 20. So it's impossible to go over all of them. So mathematically it will be secure, but the problem is that in practice, you will use it in a language like English, for example, or Hindi or whatever. Then the way languages have evolved, languages have a very, I mean, you can do a statistical analysis and see which alphabets appear more frequently. Like E appears more, A appears more, Z appears very rarely. So by a frequency analysis, you will know that in C, the alphabet which appears most is E. And slowly you will learn about pi. Okay, so you can look at few messages from Alice. I mean, Eve can look at few messages from Alice and deduce the whole permutation pi. So it can be decoded. It can be attacked. So using many m's, which are English texts, let's say. So any human written a meaningful text. The frequency analysis helps recover or helps break pi. Or break the secret. Okay, so basically you look at 5 or 10 ciphertexts, each of them correspond to meaningful messages, and just doing a frequency analysis, you will learn that what are the letters which are appearing frequently in C, and then you can map it back to what happens in usual English texts, and that will break the secret. You will know pi. Where is A going, where is B going, C, D, E, and that will basically give you the something close to the message, and then again, you using your English intuition, you can complete the message. So for practical purposes, you will have broken the code. Okay, so this is the problem. So it can be mathematically secure, but very easy to break in practice. So substitution cipher is completely broken. So we'll use more complicated things, and ultimately we'll use number theory and algebra to design the best ciphers.